So we'll look at another example of a problem that can be solved by dynamic programming, and this is called the longest common subsequence, or LCS problem. I'll first describe what the problem is and how we might use dynamic programming to solve it. So the problem is you're given two strings over some alphabet. So let the first string S be denoted as S1, S2 up to Sm. The S1, S2, etc. are the symbols in the alphabet, and the whole string is just a concatenation of these symbols. You all know about the string data type from your Java, so this is the same idea. String is just a sequence of symbols. And T equals T1, T2 up to Tn is a second string. Strings could be over the English language. The example we will see will be strings over English. But one of the reasons this problem is very important comes from biology. So one of the common things you should think about is that these strings could be characters in the DNA sequence of two different organisms, for example. So the goal is, given those two strings, to find the longest common subsequence between them. What does that mean? So what's a subsequence of a sequence? A subsequence is any sequence of letters that occurs in that order in the given string. And the letters do not have to be consecutive. They just have to occur in the same order. And a common subsequence between two strings is a subsequence that appears in both of them. So example, if you take the string S to be the string Tucson, Tucson, and the string T to be Houston, Houston, then you might find a common subsequence like this. TON, marked in red in this picture, shows you that TON is a subsequence of Tucson because it occurs in that order in the string Tucson. And TON is also a subsequence of Houston because it appears in that order in the string Houston. This is not the longest common subsequence between them, however, because you could actually create a longer one by choosing the subsequence USON, which occurs in Tucson and in Houston, and it's of length 4. Turns out that this is actually the longest common subsequence between these two strings. You can imagine this is not easy to figure out if you're given really long strings, and this is where dynamic programming comes in handy, finding the longest common subsequence. I'll briefly talk about the relevance of this problem to biology. So if you're given two sequences representing genes in two different organisms, let's say mice and humans, then finding a common subsequence between them might tell you something about how far evolution has proceeded between mice and humans. How far apart are they? So it gives you a notion of distance between organisms by finding common subsequences between the sequences for two different organisms. Actually, there are much more sophisticated variations of this that occur in biology, but the basic idea remains the same. It is the problem of finding the longest common subsequence. So can longest common subsequence be solved by dynamic programming? So let's try to do it and then ask ourselves whether it had optimal substructure and so on. So we ask ourselves, what top-level question might we ask given two sequences? So the question must be such that its answers, the possible answers, cover all possible solutions. Recall that in the problem of locating stations on a train line, the top-level question we asked was, how many towns is the leftmost station going to serve? And we considered every possible answer, one town to all n towns. That's going to be, we're going to find a question of the same kind where we consider every possible answer, and between them, they cover all possible solutions to the problem. So let's try one idea which doesn't quite work. This idea is, does the longest common subsequence include the last letter of both strings? Of course, the last letter can only be included if it happens to be the same in both strings. So if that last symbol, Sm, is the last symbol of the string S, and Tn is the last symbol of the string T, if they're equal, then yeah, sure, we can include them. We can include that symbol in the longest common subsequence. And if they're not equal, maybe the answer should be just drop the last symbols and recursively solve the problem on the remaining strings. We've at least nibbled away at the problem around the edges like we want to do. But is this correct? Well, unfortunately not. It's ignoring some other possible answers, which is the last two symbols in the two sequences are not the same, but we want to drop one of them and keep the other one. We need to allow for that possibility as well. So this doesn't cover all possible solutions. So let's come up with a better top-level decision to make. But before we make the decision, let's prove a little fact that will be useful in how to solve this problem. So the fact is the following. We call it a lemma. If the last two symbols of the two strings are equal, that is, they match, there is a longest common subsequence that uses these symbols and in fact ends in that symbol. And the proof of this is a simple proof by contradiction. It's a proof technique that I hope you've seen before. Suppose both strings have X as their last symbol, but we find a longest common subsequence that does not end in X. It ends in something else. Well, that means the longest common subsequence did not use X from either string. So we could take that subsequence we are given and add X to the end of it and create a longer common subsequence because that X is available to use. And that's a contradiction because we're supposed to have had the longest common subsequence. So it cannot be that there's an X at the end of both strings and the longest common subsequence does not end in X. But in fact, if it uses an X from a different occurrence in one of the strings rather than the last occurrence of X in one of the strings, we could switch that to making it the last occurrence and we would not change the LCS at all. So without loss of generality, we can assume that the last symbols, if they agree, can be used as the last symbol of the longest common subsequence. So that lets us come up with a better top-level decision. So if the last symbols don't match, we have two possibilities. We could drop one last symbol from the last symbol from the first string from consideration, or we could drop the last symbol from the second string from consideration, and we'll consider both possibilities. Of course, if they match, based on the lemma we just proved, we'll just use the last symbol in the longest common subsequence and recurse on the remaining strings. And we are not ignoring any possibilities here, because if the last symbols do not match, we do have to drop at least one of them. They cannot both be in the longest common subsequence. So let's now, with that understanding and that top-level question, let's set up some notation. So let LCS ij represent the length of the longest common subsequence using the first I symbols of S. S, remember, is the first string we are given, and the first J symbols of the second string T. So we're just going to let LCS ij be the length of the common subsequence between these pieces. So between what and what? The first I symbols of S means that between the string S1, S2, up to Si, and the string T1, T2, up to Tj. So we're going to look at the length of the longest common subsequence between these two and call it LCS ij. We're just going to store the lengths, but we could, if we want to, keep track of the actual sequences by keeping some additional bookkeeping information. Actual common subsequence. So then, based on what we've said earlier, what we're saying is that the last symbol of the first sequence is Si, and the last symbol of the second sequence is Tj in the sub-problem that we're dealing with. If these last symbols match, we might as well use it as the end of the longest common subsequence between these two strings. And if we do that, then the longest common subsequence ij is the one from the matching of the last symbol, plus the length of the recursive solution you get using the first I-1 symbols of S and the first J-1 symbols of T. Basically, we've nibbled away the last symbol from both strings. If Si and Tj don't match, then we've got to drop one of them. So LCS of ij now is the best you can do by either dropping the ith symbol from S and just working with the first I minus 1, or dropping the jth symbol from T and working with the first J minus 1. So that's denoted here as the max of these things. So that's the recurrence relation for this problem. All recurrence relations need like base cases where we don't recurse further. What are the base cases here? We can write a simple recursive algorithm to implement this, but so we will see the base cases in a minute. So we should start. So let's start with the smallest subproblems of the base cases and then build up to bigger solutions. So what does LCS of I0 or LCS of 0j represent? LCS of I0 says take the string S1, S2 up to Si as the prefix of S that is I symbols long, and take the empty string as the second string. 0 means you don't have any symbols, so basically you have an empty string as a second string. What do you think is the longest common subsequence between some string and the empty string? Well, obviously you cannot there are no symbols in common between these two. The empty string has no symbols at all. So the longest common subsequence has length 0 in both cases. So those are the base cases beyond which we don't need to do any recursion. So if one of our strings is empty, the LCS must be of length 0. So what is the subproblem that's the solution to our whole problem? Well, we want to find the longest common subsequence between S1 through SM and T1 through Tn. So in fact, it's actually, this is a little typo here, this is M and this is N. So we want to find the LCS of M comma N, the longest common subsequence between SM and Sn, and S1 through SM and T1 through Tn. So this time we're going to design the dynamic programming algorithm from the bottom up. So meaning we're going to start with solutions to the small problems and build our way up. We already know that if one of the arguments to LCS is 0, it's either LCS of 0j or LCS of I0 for any value of I and j, then the solution is also 0 because there is no common subsequence of any length with the empty string. So we'll start there. And we will, as before, we will try to keep track of the problems we've already solved, the solutions to the problems we've already solved, so that we don't keep recomputing solutions to the same problems again and again for efficiency. So to do this, we can actually create an m plus 1 by n plus 1 grid. Why m plus 1 by n plus 1? Well, if you look at the string S, it has m symbols in it, S1 through Sm, but we also want to allow the index into this string to start at 0, because that's the base case we know how to solve. So the rows are going to be indexed from 0 through m, and the columns are going to be indexed from 0 through n. And if you think about it, that's m plus 1 by n plus 1. We can fill out the leftmost column, which is where j has value 0, as all zeros. Basically, the leftmost column represents the length of a common subsequence between some portion of S and the empty portion of T. And so that's all zeros. Similarly, the topmost row can also be filled in with all zeros because that represents the common subsequence, the longest common subsequence between an empty substring that represents for S and some portion of T. And that we already saw was 0. So we start with this grid with the top row and leftmost column already filled in, and we're now going to fill in this grid row by row or column by column, whichever way you like, using the recurrence that we just created, that we showed last time. So LCS length ST, so M is the length of the string S, N is the length of the string T. So M is an m by n matrix. That should really be an m plus 1 by n plus 1 matrix. So for I equal to 1 to m, I would actually go from 0 to m because we do have to take care of the symbol 0, the index 0 as well. For I equals 0 to m, mi0 gets the value 0. For j equals 1 to n, again, that should be 0 to n. M0, J gets the value 0. This is just initializing, filling the top row and the top column, top row and the leftmost column with zeros, as we said earlier. Now for I ranging from 1 to M and for J ranging from 1 to N, and here we are filling things row by row because we're letting J run through all the possibilities while keeping I fixed. The inner loop is ranging over J. So if the ith symbol and the jth symbol match, Mij, the LCS of Ij, basically the length of the longest common subsequence between the first I symbols of S and the first J symbols of T, is just the solution where we nibbled away the last bit of both, last symbol of both S and T, plus the 1 for the match you get on the last symbol. If Si does not match Tj, then Mij is the maximum you get out of two possibilities, either dropping the last symbol of S or dropping the last symbol of T. This is dropping the last symbol of S, and this is from dropping the last symbol of T in the subproblem we are considering. So we compute in this manner and we return the value at the location M, N. So the total running time of this algorithm, or for any dynamic programming algorithm, is roughly speaking the number of subproblems you have times the time it takes to solve each subproblem, to compute the answer to each subproblem. How many subproblems do we have? Well, this is pretty nicely laid out for us here, because if you look at the grid has about has exactly m plus 1 by n plus 1 times n plus 1 cells. And each cell corresponds to a subproblem. So the number of subproblems is m plus 1 times n plus 1. For the time it takes to solve a subproblem, you can see that it's just a few steps. If for any subproblem ij, we do one if then else, and within each, if the then clause and in the else clause, there's just one statement that's executed. So this is what's called constant time or order 1 time to solve any one subproblem. Order 1 is just a fancy way, asymptotic way of saying it's constant. So if each subproblem takes constant time and there are about mn subproblems, the overall running time is going to be order mn. So this is a very efficient algorithm that runs in time proportional to the product of the lengths of the two strings for which we want to find the longest common subsequence. Now that we've seen the algorithm for the longest common subsequence, let's see how it would work on the original example that we gave of finding the longest common subsequence between the two strings Tucson and Houston. So I've set up the table here, and as I said in the algorithm, we can initialize the table to say that the longest common subsequence between the empty substring of Houston, that's the top row here, that corresponds to the empty substring of Houston, and any substring of Tucson, any prefix of Tucson, the longest common subsequence is of length 0, because there's no symbol in the empty subsequence, and so obviously you cannot find a common subsequence with any symbols in it. Similarly, you can take the empty subsequence of Tucson and compute its longest common subsequence with any prefix of Houston, and the answer is also 0. So we fill the table with the first column and the first row being zeros, and now we compute new entries of the table, maybe in a column by column fashion. So we're doing the first column first. And what do we do for any entry in the column? Let's go on and I'll show you an example further down. So we're filling this table column by column. So let's look at, for example, this entry here. So that is corresponding to the longest common subsequence of TUCS and HOUS. Now this is the case where the last symbol of Tucson and the last symbol of Houston, the prefixes right now, TUS and HUS, the last symbols are S in both. So we can match them for sure, as we saw in the lemma. We can always match the last symbols if they agree, which they do in this case. So we match these two. And now, so that gives us a score of 1 for the longest common subsequence. And then we have to find the longest common subsequence between the previous part, TUC and HOU, which answer can be found in this entry. So we take whatever the answer is for this entry and add 1 to it to get this entry. So we get the 2 that way. Just as another example, suppose we consider, let's go one more column down. So suppose we consider this entry here. That is considering the longest common subsequence between the string TUCSO for Tucson and HOUST out of Houston. You see that the last symbol for the two strings is not the same. It's O versus T. So obviously you cannot match them. So the choice is to either delete the last symbol from one and use the best sequence you can get from the rest of it, or delete the last symbol from the other and use the best sequence you can get from the rest of it. So if you delete the O from Tucson, you find that you can take this entry, which is TUCS matched to HOUST, and of course you don't get any extra score because you're not matching anything more. So you can take that score directly and put it here, or you could delete the T from Houston, and then you would use this entry, and again you can take the 2 and get that same score. You cannot improve it because you're not matching any more symbols. So the score in this entry, this original entry I was interested in, this one here, is the maximum of the score I can get from the left plus 0, because I don't get any extra credit for matching anything more. And that score is only 2 because these are both 2. So either way I get 2. Okay, that's how this table goes. So we fill this table up, and at the end we find that the longest common subsequence between Tucson and Houston has length 4. Now, how did I get the 4? Well, you can actually trace it back and say, well, obviously this 4 came from the 3 here, because from the diagonally above 3, because if it came from above or to the left, it wouldn't have increased by 1. So that means this corresponds to matching the last ends of Tucson and Houston. So I match the last ends of Tucson and Houston, and I use the length 3 longest common subsequence of TUCSO and HOUSTO. Now, again, the O and the O match, so I could get that score by taking the diagonally above entry 2 and adding 1 to it for the O match. And again, now you have the longest common subsequence of HOUST and TUCS. So now we realize that the last symbols don't match. Where did this 2 come from? It must have come from here, because that's the only one that's equal to this 2, and that corresponds to dropping the T from Houston. So we are now looking at matching HOUS and TUCS, and now you see that the last symbols are S in both, so they match, and so this came from here. So now we see that this 1 comes from the longest common subsequence of HOU and TUC, and so on. So if you continue like this, you can actually trace back which symbols were taken in creating the longest common subsequence between Houston and Tucson, and why we got this score of 4 at the end.